In this mini lecture, I'm going to talk a little bit about the ideas of half-life and doubling time. So sometimes with exponential growth and decay, we focus on things like population growth, but there are some quantities that decrease over time instead of increasing over time. And some common elements, such as carbon, they occur in different forms in the natural environment. The most common form is called carbon-12, and that's stable. So what that means is if you have an amount of carbon-12, it stays constant over time. You just have 100 grams of it, you always will have 100 grams of carbon-12. However, there's a naturally occurring form of carbon called carbon-14, which is actually unstable. So what that means, over time, it changes to a more stable element. Carbon-14 is an example then of it's a radioactive isotope of carbon, and all radioactive isotopes, not just carbon-14, but all radioactive isotopes have something in common, something called a half-life. So the half-life of a substance is the amount of time required for just 1/2 of a starting quantity of that substance to decay. Now, that doesn't mean, when I was first learning this, I thought somehow that meant the substance disappeared or something. Of course, that's not true. Matter is neither created nor destroyed. What happens is that the substance changes into something else. So let's say a substance has a half-life of 3 hours, and we start with 100 grams of this substance. Here's how the quantity would change over time. So at the beginning, we have 100 grams. After 3 hours, that's one half-life, we'd have only 50 grams, half of 100. After another 3 hours, the 50 would change to 25. I'd take half of that. After another 3 hours, I get another half, so I'm down to 12.5 grams. And after another 3 hours, I'm down to 6.25 grams. So after 12 total hours, that's 1, 2, 3, 4 half-lives, I'm down to 6.25 grams. Now, in theory, this process never stops. I mean, we'd keep going, and we'd have smaller and smaller and smaller amounts, and it would never reach zero. In real life, of course, once we get down to a really small number of atoms of this substance, this behavior may not occur exactly the same way anymore. It turns out that we can use this general exponential growth and decay model to describe this type of occurrence that we have here. To do that, though, I need to figure out what this value k is. That's the decay rate. The technique we use to do this is we replace t with the half-life. So we would say here, let's let this go 3 hours. And then how much am I going to have? Well, I don't know what I was starting with for A0, but after a half-life, I'm only going to have half of it. Half of something is a half times something. So a half of the original amount would be a half of A sub 0. That would be a half times A sub 0, or 0.5 times A sub 0. So I'm going to replace this A with 0.5 A sub 0 and then solve for K. So here's how it would work for this substance here. So I start with the model. A equals A sub 0 e to the kt. I'm going to replace A with 0.5 A0. And I'm going to replace T with the half-life, which is 3 hours. Okay, so those are the substitutions I've made. I've put in 0.5 A0 and I put in the 3 hours. Now I'm trying to solve for K, and K is up here in the exponent. I'd like to take it out of the exponent. One way I can do that is if I have the log of e to a power. But what's going to mess me up right now is this A sub 0 in front of the e. So I'm going to have to get rid of that. So what I'm going to do is I'm just going to divide both sides of this equation by A sub 0. What's going to happen then, the A sub 0's are going to cancel out on both sides of the equation, and I'm going to be left on this left-hand side with just 0.5, and on the right-hand side, e to the 3k. So then I'm going to take the natural log of both sides. So natural log of 0.5 equals natural log of e to the 3k. That 3k can come down in front. So we get natural log of 0.5 equals 3k times the natural log of e. Remember, the natural log of e is really the log base e of e. So this whole thing says e to what power is e which means this whole thing is actually equal to 1. So I don't have to mess around with that anymore. I'm just going to have natural log of 0.5 equals 3k, and then to get k by itself, I would just divide by 3. And so we would get k is the natural log of 0.5 divided by 3. And whatever decimal that ends up being, that would be this decay rate. Now I could use this model here, but I could replace k with whatever decimal I get from this calculation. This works for many other quantities that decay over time. One big application is something like medication in a person's bloodstream. When you first take a medication, that's absorbed in your bloodstream, and that goes up over time as it gets digested. For instance, if it's a pill or something, if it's a shot, it's pretty much in your bloodstream right away. But what happens is your body starts to metabolize that medication, and so it starts to change into other substances, and we would use a half-life to talk about that. Now, something sort of related to this is an idea from investing, and it's something called a doubling time. So the doubling time for an investment is the amount of time that's needed for the total value of the investment to double. So instead of having a half-life where I end up with 50% of the starting amount, here I'm going to replace A with 2 times A0. So that gives me twice the starting amount, and then solve for T. So here's the calculation. My general model, A equals A sub 0 times e to the kt. I'm going to, like I said here, replace A with 2 times A0, and k is going to be replaced with the interest rate as a decimal. So instead of A, I'm going to put 2A0. That means I'm going to end up with twice the original amount. I'm starting with the original amount. My interest rate is 8%. I have to put that in as a decimal. And now I'm going to solve this. I solved this the same way I solved the problem on the other page with half-life. I'm going to get rid of the A sub 0 so that that cancels out. So now I get 2 equals e to the 0.08t. I'm going to take the natural log of both sides. That t looks horrible. 0.08 t. I'm going to take the natural log of both sides. Because now I can bring that exponent down in front. And like before on this other page, the natural log of e is just equal to 1, because e to the e power is 1. So natural log of 2 equals 0.08t, and I would just divide by 0.08 and get that result there. If we figure out what this t is, I don't have a calculator right here. If we figure out this t, though, it's about 9. It would be about 9 years. And you can check that on your calculator. It's not exactly 9, but it's somewhere around 9. Note that this doubling time is approximately 72 divided by the interest rate. If we said it was an interest rate of 8%, 72 divided by 8 is 9. This is sometimes called the rule of 72, and it works for all interest rates. We just take 72, we divide by the interest rate, that gives me the approximate doubling time. And I've illustrated here why that works. So I start out with my basic function, my basic exponential decay model. I replace A with 2A0. That's where I want doubling time. I divide by A0, I get this here. I take the natural log of both sides. That brings the exponent down in front. The natural log of e is just 1, so that goes away. So t is just going to be the natural log of 2 divided by r. Notice that's what I had up here, natural log of 2 divided by 0.08. Natural log of 2 divided by r. Well, the natural log of 2, if we do that on our calculator, it's about 0.6931. And so if I multiply top and bottom by 100, that changes that to 69.31. And if I get r times 100, well, that was a decimal times 100. That's going to give me r as a percentage. Well, 69 is pretty close to 72. Why is that correction made? Well, a lot of numbers divide into 72 easily. I don't know what 69 divided by 8 is, but I know what 72 divided by 8 is. A lot of numbers go into 72 evenly. 2 does, 3 does, 4 does, 6 does, 8 does, 9 does, 12 does, right? A lot of values go into 72. If I have an interest rate then of, say, 4%, and I want to approximate the doubling time, I would take 72 divided by 4, and that would be a doubling time then of about 18 years. So that's a nice thing to sometimes keep in mind. This works not only for investments, but also something like a country's overall economy. So if a U.S. economy is growing at a rate of 4% per year, it will take about 18 years for the total U.S. economy to double.